All right, we're on section 10.7, and I've already got a circle drawn right here with two what? What would those things be called right there? Two chords, right. And they intersect. Where do they intersect? In the middle? Is that what you want to say? Inside the circle, right. It's just inside the circle, okay. We already had a theorem, did we do this yesterday, day before, where we had two secants intersecting inside the circle? What did we say? We talked about the arcs, didn't we? Remember we said this arc and this arc, if you add them up and take half of it, that's what this angle is right here, okay? This is different though. We're not talking about the lengths of the arcs or the angles, we're talking about the lengths of the actual segments themselves. So this is technically, I guess you could consider it a secant if it kept on going, but it's two chords because it starts and stops on the circle. It's two chords and we're finding the lengths of them. You can't really find the length of a secant, can you? Because it's a line, it just keeps on going. But these are two chords that intersect inside the circle right here. Let me put some letters down. Oops, let's click on here. All right. Let's just call this A. I'll go different color just to jazz it up a little bit. So we'll call that line segment A. If I just put an A right there, it means from the circle to the point of intersection. Everybody understand that? This one right here is B, so that goes from the point of intersection to the circle. I don't have to like put little lines there, you know. All I got to do is put an A there, you know it means this segment, and B, that means that segment right there. So I'll call this C and D. Now here's the theorem. The theorem's pretty easy. I don't know if you could just look at this and tell what it is. We're not going to really go through and show you why it does this, but here it is. If I take the product of the two segments of this chord, it's going to equal the product of the two segments of the other chord. Tried to say it slow. It's a mouthful, isn't it? But did you understand what I said? Yeah. What does product mean? Multiply. So if I take this segment, multiply them together, what would I get? AB. That should equal the same thing on the other one, CD. Exactly right. That looks pretty simple, doesn't it? There it is. That's your theorem. Okay, everybody got that? All right, let's do a quick little example with this just to see how to do this, and we'll move on to the next one. Pretty easy. All right, now I got rid of the A, B, C, D. Let's put some numbers in here. Let's say this is 5 and this is 12. Then say this is X and this is 10. Not necessarily drawn to scale, but who cares?
X is 6.
All right, let's do this. What we're going to do is we're going to set it up in this form right here. We're going to take the product of the segments. So let's do the first one. Let's do the X first because it'll make it on the left-hand side. So if I multiply those together, pretty easy. What do you get? 10x equals 5 times 12. This is pretty easy. It's not brain surgery here. Then divide by 10. And Tiffany, you said it already. What is it?
6.
It's 6. Okay. And there it is. So what's that? It's not 10 plus, it's the product. These are not being added together. It's being multiplied together. It's 10 times this. It's not 10 plus. It's 10 times this. All right, equals 10 times this. You got it? So this is 6. So that chord right there is 16. This chord right here is 17. Does it necessarily mean the chords are equal to each other? No, not at all. That doesn't mean the chords are equal to each other, but the product of the segments of each chord are equal to each other. Make sense? All right, let's do another example, a little bit harder than that one. All right, we're going to do this again, but I'm going to keep the same circle. No reason to draw a different circle. I'm just going to put different values for this. Is that all right with you? Again, it's not necessarily drawn to scale. I'll make that x plus 1. I'll make this one. Actually, I just said I wasn't going to make it to scale, but that bothers me. If this is x plus 8 and this is x plus 1. All right, let's do the other one, x plus 10 and x. We'll call this x and we'll call this one x plus 10. So what we want to do now is we want to solve for x, obviously. So we just set up the exact same situation that we did before. We set the product of these. Now the math is a little bit different on this because look, it's x plus 8 times x plus 1. We just talked about this the other day, didn't we? Okay, FOIL method, that's right. And this is going to be x times x plus 10. So the geometry wasn't hard. It's the same exact geometry as what we did before. It's just the algebra is a little bit different. All right, and let's figure it out. Let's do the FOIL method. We'll do it real quick here. You can look back and figure out how we're doing this. This is x squared plus what? 1x plus 8x, which is 9x plus 8 equals, distribute the x through that one, so we get x squared plus 10x. Check this out. What happened to the x squareds? Yeah. We say cancel all the time, but really, what are we doing to them? I just want you to understand that. We're subtracting them, right? Okay, I like to say that better, don't you? We say cancel for a lot of different stuff, but it's nice to know what you're actually doing. You're actually subtracting that from both sides. Now, what can we do? Get x by itself. We can subtract a 9x from both sides, so we get an x over here. Everybody see that? I just didn't show the step, but subtract a 9x, subtract a 9x. That's a 1x, and that's an 8, so there you go. X is equal to 8. That's all there is to it. That looks kind of weird. I always like to write the x first, don't you? So there you go. X is equal to 8. That's it. It doesn't ask you the lengths. It could, though, couldn't it? I mean, that could be a question. They say, what is, they could label this, A, B, C, and they say, what's the length of segment AB, or the whole chord AC, if they wanted to. Right? If you know X, you can find any of those things, can't you? All right, that's not that big of a deal, but they could ask you that. All right, let's move on. That's the first one. We're going to do 3 of these different theorems right now. That's the first one. Pretty simple, not that big of a deal. The second one's maybe a little bit more confusing. Not much, but a little bit more. This is probably the easiest, definitely the easiest of the 3. All right, so let's go on to another one. Okay, we just did 2 chords that intersect inside the circle. Now we're going to do 2 secants that intersect outside the circle. We did that yesterday too, didn't we? All right, but what did we talk about? We talked about the angle and the arcs. This time we're not talking about the angle of the arcs. What do you think we're talking about? The what? Not the arcs. Come on. What did I just do before? I just said earlier in the other one. I didn't talk about the angles, right? I'm talking about the lengths of the either chords or whatever it is, the segments. Okay, I'm talking about the lengths of the segments, not about the angle, not about the arcs. I'm talking about the lengths. And so what I'm going to do is draw a secant. Now, again, technically a secant keeps on going forever, but we're just going to go from one point to the other. So we're not talking about the whole entire line. We're just talking about the line segments that are made. But these are secants, though. I mean, they are going through the circle, hits it at 2 points, and so, yeah, they're definitely considered secants. All right, how should I do this? Let's label it with letters again. I'll use the same letters that they use. They use A, B, and C, of course, and D and E. Now, this again is 2 secants that intersect outside the circle. It's the only time this works. What we're going to do, if you look at it, we could have this thing keep on going through. I'll tell you what we're going to do, because I'm not going to talk about this segment right here. The only thing I'm going to talk about is from where the points intersect to this end point right here on the circle. So this, I can just kind of move until it's right on the circle itself. Come on, right there. And we're going to do the same thing with this one. We're going to move this so it's right on the circle. That one's a little bit off. I know I'm being a little picky here, but that's okay. There we go. That looks a little bit better. Now look at the segments. I've got segment what? What would we call this segment? Talk to me. Now just this one right here, what I'm pointing to. AB. Okay, now say it. This one is BC. This one and this one DE. All right, you got it? So we're going to talk about those. Now watch. The theorem's just a little bit different. What we do is I talk about the outside segments, the inside segments, and the whole segment. All right? Basically, I'm going to talk about the outside and the whole because that's what this has to do. So if I said the outside segment of this secant right here, which one would it be? The outside segment of this secant, what would it be? AB, because it's outside the circle. You follow me? What if I talked about the whole entire secant? This one right here that I'm pointing to. It's AC, right? This is a C right here. So it's AC. So our theorem basically says this. This is how I say it. I'll write down exactly what the theorem says in terms of these letters, but this is how I say it. I say you take the whole secant times the outside segment. All right? So what's the whole entire secant then? AC. So I take the whole entire secant, AC, all right, line segment AC, and I'm going to multiply it by the outside segment. Which one's the outside segment? And let me see how they do it. Yeah, they do it with a little dot right there. So it's times AB. And you really actually don't even need this, because if you don't have that bar over it, it's talking about the length of those segments. So that's probably better to write it like that. Now watch. If we did that here, this is the whole thing, right? And this is the outside. I'm going to just write the next part down, then we'll go to the next lesson. So here's the whole thing times the outside. What would I write here then? What's the whole thing on this one? AE. And what's the outside part there? AD. All right, and we'll do an example here in a second.